I'm going to be talking about our work on parallel window decoding and how it enables scalable, fault-tolerant quantum computation. This is a work from a group of authors from Riverlane. Sorry. So sticking with the River theme, we're going to start at the source, which is that many of you might appreciate that fast decoding is important, but here I'm going to discuss why it's essential for practical fault-tolerant quantum computation. Then we're going to get into some tributaries, which is the current leading proposal for real-time decoding. That's a sliding window method. And I'll discuss why this method is inherently not scalable. Then in the main channel, I'm going to discuss our proposed solution to this, which is the parallel window decoding, and some of its implications. And then finally, we are going to flow into the delta of the river and discuss how the parallel window method affects decoding speed of a hardware decoder that Riverlane is working on. So starting from the source, why is fast decoding essential? So surface code is going to be the focus of this talk, but methods are applicable possibly to other codes as well, and this has been introduced in previous talks, so I'll just quickly review it here. Surface code is described by a planar patch of stabilizers with two logic operators on it, X and Z. And in decoding in general, we have a syndrome that is given by here these stabilizer checks, and we need to find the effect of the most likely error that is consistent with the syndrome. So in this case, on the picture, we have a few syndromes that are that light up, and this can be explained by having an X error here and a Z error here. The effect of this error is that Z logical is flipped, and the success in decoding means that the correction has the same effect on the logicals as the error. But syndromes themselves can be noisy and can have errors. So we need to take that into account, and we need to repeatedly measure these stabilizers, which at the end creates a decoding graph that is what we call 2+1D, or a 3D decoding graph, where time is going up. Data errors are horizontal edges, and measurement errors are vertical edges. Here, for simplicity, I'm only describing phenomenological noise, which means we trigger syndromes we introduce errors at random at each point, but we also need to consider, in more general case, circuit level noise, so all of the effects of any error that can happen in syndrome extraction circuit, but all of the methods here are equally translatable to that case as well. But we need to do, so this would describe how we are decoding graph for the memory experiment, but we also need to do operations. So why do we need real-time decoding? Well, we'll first consider Clifford circuits, which include situations like quantum memory, that was shown before. And when I'm showing circuits here, I would just like to mention that the lines are always logical qubits that are represented by, say, surface code patches and potentially consists of many physical qubits. And in the case of Clifford circuits, as long as we can detect where errors happened, we can always commute these errors through the Clifford operations and reinterpret any measurements. This means that as long as we store the syndrome data, we can always decode this later and reinterpret the measurements, and then we can just decode in post-processing, and that is sufficient. But that is not enough. Clifford circuits are easily simulatable on classical computers and don't give us any quantum advantage. So we need to do more, and we need to be able to do non-Clifford circuits as well. If you want to implement non-Clifford circuits in a fault-tolerant manner, such as T-gate here, these types of gates usually are implemented with circuits that use some sort of classical feedback. So in this case, we initialize a magic state fault-tolerantly, and then do a teleportation circuit on it to apply the T-gate on our logical qubit of interest, which is this psi. This teleportation circuit consists of a C0 and a Z measurement And then we need to apply, depending on the result of that Z measurement, S gate. So this is going to introduce dependence on the Z measurement in the circuit. That because these are logical qubits, we need to, and it consists of patches of syndrome extractions. To get the accurate measurement here, we need to decode all of the data that came before the measurement, and then reinterpret the measurement based on that. So in this case, we need some sort of live feedback to be able to implement multiple gates like this sequentially. So how fast does this feedback need to be? How fast do we need to run this real-time decoder to be able to perform these gates? So in general, we can assume that decoding time scales linearly with the number of error correction rounds, which is true for most decoders. And then we can define this factor F, which is a ratio of how quickly the syndrome data is coming in and how quickly versus how quickly we are resolving that data. So if F is bigger than 1, that means that our decoder is slower than the data that's coming in, and we're going to start creating some backlog as the computation progresses. So suppose that's the case. Suppose that we are slower than the syndrome acquisition speed. So while we're waiting, when we apply the circuit and we get this measurement, we get this data that we need to decode before we can apply the S-gate correction. And how long we need to wait here is determined by this factor F, and we need to wait Ft minus T. So this is a lower bound given by our decoder on this, how quickly this feedback can happen. But while we're waiting, as we said, the backlog is accumulating because we can never stop measuring stabilizers on our logical state of interest here. So next, when it comes to applying the next T gate, now we need to start decode this backlog and then decode all of the data that is accumulated when we apply the C0, again, the same C0 and the same Z operation, before we can apply the next correction, the next classical feedback. And this is going to introduce another factor of F in the time that we need to wait for the next gate. And if we extrapolate that, the nth gate is going to take at least F to the nt, and that means that we're going to introduce an exponential slowdown, and each sequential T gate is going to be a factor of F slower, as long as our F is bigger than 1, which means our decoder is slower than the data acquisition. So let's see what this means in practice. If we have a superconducting computer, that computer is acquiring syndromes at about a rate of 1 microsecond per round, so we get a set of stabilizer measurements every 1 microsecond. And if we want to simulate something like a FEMOCO molecule, which is a common molecule quantum chemists might be interested in, we need approximately 10 to the 10 T gates. So this would take about a few days to run if we assume no feedback lag. And then say our decoder is about 1% slower than the syndrome acquisition time, and it takes about 1.01 microsecond per round to resolve the data. So our F is 1.01. In that case, with the lag, the time it takes to perform this computation is way longer than the age of the universe. And you can quickly see how if we can't stick to this very strict requirement that we need to be faster than the data that's coming in, quantum computation is not going to be possible in practice. And what makes this even worse is that decoders take longer for bigger codes. So the bigger the code is, usually this factor F is going to scale linearly with the number of qubits. And if we want to perform a very long computation, we really need big codes because we need to stop the state from decohering, which means that we have slower decoding, and eventually that's going to lead to a backlog problem. So this means that there is a maximum limit on the size of quantum algorithms that we can execute as long as we have this linear scaling. So we see that we really need fast decoders, and we really need decoders that can resolve very big codes. So I'm going to now discuss the sliding window method, which is the current proposal how to do this real-time decoding. So in this in this schematic on the left, the time is going up, and here we're representing, as an example, a repetition code, or you can think of each horizontal slice as a slice of a surface code, where green points are the triggered syndromes, so give us information about the errors in the system. The problem is, again, matching up the syndromes using the set of edges that has the least weight. And the horizontal edges here, again, representing data errors, vertical edges representing measurement errors. So we can decode this by considering this whole big block as one decoding problem. But if we have a very large number of rounds, this becomes unfeasible, and we need to somehow break it apart. The way we do this conventionally is take a window of the data, so a subset of the data, and decode that first. The problem with that is that at the edges of the window, so in the last rounds, we don't know what happens, what syndromes might come next that might affect our decoding around the top of the window, so in the latest rounds that we're considering. So we can't commit to that. The stuff that we are more confident about are the corrections that our decoder gives us in the bottom part of the window, which are further from this edge. So we separate the window into a buffer region and the commit region, where the buffer region gives us the context necessary to give confidence on the corrections that we have in the commit region. So we decode this, get the correction edges. Any edges that are going from the commit region to the buffer region are committed only to the edge of the commit region and give us additional artificial defects that are then resolved later on. And then we keep sliding this window up by half the window size, and we have this overlapping a set of overlapping windows that are slowly moving up through the computation and decode the data as it's acquired. So we again take the window, commit only to the commit region, and keep moving it up until we get resolve the whole computation. Here, it's also important to mention that this buffer region needs to be large enough when we're creating our window so that we have big enough context for the commit region. And in general, this means that we need to have about equal protection against space-like errors as we have against time-like errors. We need the buffer region to be about the size of the distance of the code, so that any string of errors starting in the commit region is guaranteed to be within the window that we are decoding. And if we do this way, we don't expect to have a drop in accuracy, as opposed to decoding this as one big problem, which would be the most optimal thing to do. And we simulated this, and that's exactly what we see. So on the left plot, we are considering the global decoder, which is the lines here, so taking this whole thing as one big problem that we resolve all at once, as opposed to the sliding window, which are the points for a number of different code sizes, and looking at how the logical error rate changes as we increase the number of rounds. The fact that points here correspond to the lines tells us that there is no noticeable loss in logical accuracy if we use sliding window method, so real-time decoding versus using the global decoder. What we also see is that as the code size is increased, each window gets bigger, and there is more, the problem within each window is harder, so the decoding speed reduces as we increase the code size. This means that eventually we're going to inevitably hit the backlog problem for big enough codes. So this means that the sliding window method does not allow us to go to beyond certain code size, as long as we have decoders that are slower for bigger codes. Now I'm going to discuss our solution to this problem, which is the parallel window method. And if you're interested in this, there is also another paper that came out the same day as ours that has many complementary results from the Alibaba team. So if you're interested in our work, please take a look at theirs as well. So as we decode with the sliding window, if we're too slow, we amass this backlog. Data is coming in while we're trying to resolve the window. We can't stop it, and we get the backlog that just we can't keep up with, and that's building up throughout the computation. So one way to deal with it is to consider how we're doing the decoding. We can split the decoder into having an outer decoder, which defines how we are dealing with, how we are chunking up this data, and the inner decoder, that is one of the classical decoding solutions like minimum perfect matching or union find that resolves syndromes within the window. And here we had the global decoder, which just considers everything as one big problem. Previously, we had the sliding window decoder. But what we thought of is, while we're having this data, is there something that we can do with the data before the window has caught up with it? And can we do this in parallel? So in our scheme, the outer decoder actually splits up the problem into a multiple of non-overlapping windows. And because they're working on different data, they can be resolved in parallel. The problem here is that now we're not sure what syndromes are coming before the window, as well as syndromes that are coming after the window. So we need to introduce these buffer regions both at the top and at the bottom of the window, and we can only commit with confidence to the corrections in the center of the window. But if we do that, we break the problem apart and we resolve some things that are now, or that were previously in our backlog. And then in the second step, because now the only thing that's left are these regions between the windows, we can again do this in resolve these regions in parallel. And because we are confident about the corrections that we had before each of the windows in this second layer of decoding, we can just commit to the whole window. And in this way, in 2 steps, we can decode, given enough parallel resources, the whole history of syndrome data. In reality, we have a finite number of parallel resources, but this still allows us to reduce this R factor F, or increase our decoding speed with the number of parallel resources. So looking again at the accuracy, similarly to the sliding window, if we choose our buffer regions to be about the distance of the code, we don't expect to see any drop in the logical accuracy. So as we increase that number of rounds, we again look at the logical error rate comparing the global decoder with the parallel window decoder. And we see that the points and the lines correspond. That tells us that there is no noticeable drop in logical accuracy using this method as opposed to global decoder. The advantage is, however, that we can increase the number of processes that we have, and that roughly linearly increases the decoding frequency. Now, going back to the backlog problem, we still have some lag. We need to wait for the decoder. But now that lag can be limited to 2 times the size it takes us to decode each window, because we can decode the whole problem, so the whole set of syndrome data before this measurement in 2 rounds that we had in 2 layers of decoding. So the total algorithm running time is going to be given, still going to depend on the time it takes us to decode a single window, but it's going to depend linearly, and we're not going to have this exponential slowdown, and there is going to be no backlog problem. As long as we can dedicate enough parallel resources, we can always achieve this. However, we ideally want the clock speed to be as fast as possible, so we still want as fast as possible inner decoders that are then going to allow us to be have faster clock rates. So far, we've been discussing only how we can parallelize in time to solve the backlog problem, which we identified to be this big problem in fault-tolerant computation. But we can also parallelize. In space. This is very relevant for situations like lattice surgery, where we are doing logical operations, and we can get these very long codes, which are have much bigger distance than the areas that we are trying to protect against, which make decoding very difficult. And in a similar way, we can break this problem apart into chunks that can be parallelized. But it can also parallelize in more dimensions. So we can use the similar scheme of commit and buffer regions and regions that are not touching to break, say here, a 2D or 3D problem into 3 types of regions, A, B, and C, or red, green, and blue, that are not touching. And then we can resolve all A regions in parallel with their buffers, and then all B regions in parallel, and then do the same thing for C regions. And this way, in 3 steps, we can break this much bigger 3D decoding problem into smaller windows and do it in 3 steps. So let's see how this affects, method affects a hardware decoder. So as I hopefully convinced you, the speed of decoding is essential, and it means that eventually we will need a very large amount of fast and efficient decoding hardware. That is why Riverlane is working on both FPGA and ASIC hardware decoding solutions that we envision are going to be used in the future fault-tolerant systems to do real-time decoding feedback. So we have also an infrastructure that allows us to test these theoretical decoders in simulation and deploy them in hardware. And here I'll show you some modeling data on our hardware decoder on a circuit-level noise on rotated planar code, assuming 500 megahertz FPGA. And here we're aiming for about 0.5 microsecond per round decoding, because we need to take into account that if we're doing either parallel or sliding window method, there are some rounds that we're not committing to. So we are aiming for faster decoders than this 1 microsecond threshold. Yeah, so our modeling, we're confident our modeling tools, because we are deployed these decoders in FPGA as well, and we have good correlation. So here, this is our most recent published hardware decoder, that we can see that as we increase the code size, we're plotting this as plotting decoding frequency as a function of code size for 2 different noise rates, looking at circuit level noise here. And we can see that we can decode codes up to distance 9 and even going to close to distance 11 for lower noise rates, almost getting there. But this is only on a single core. We can also now use our parallel window method to project how this would work when we employ multiple cores. So here I'm considering pretty high noise, so P equals 0.4%. That's getting fairly close to the circuit level noise threshold. And we can see that as we increase the number of cores, so here different colors are increasing number of cores, our decoding frequency is expected to go up. And we're expected to be able to decode distance 11 codes and beyond using a relatively modest number of cores, here considering up to 16 cores, but there's no reason why in the future we wouldn't be able to go to more cores. So yeah, in Riverlane, we are confident that we can support real-time decoding of near-term hardware, so pretty noisy hardware, and that we are able to scale with the hardware as the number of qubits increases. So to conclude, here we present the parallel window method that allows us to achieve an almost arbitrary decoding speed by adding parallel resources and overcomes the backlog problem. We can combine this with any inner decoder that can be minimally perfect matching, or it can be union find, or any decoder that gives us a matching on this graph. We see no noticeable loss in logical fidelity using this method, and we believe because of the simple pipelining structure of this problem, where we can just, there is very little data dependency between windows, we can efficiently implement this in hardware. And finally, I'd like to thank the authors of this paper, as well as the Riverlane decoding team that helped a lot with this work, and leadership that supported it. Thank you.
Thank you so much. So we have time for a few questions.
Okay, so how easy is it to take an existing decoder and just put this method on it?
So as long as the decoder is giving a set of edges that are matching edges between the syndromes, then yes, it can just be straightforwardly do very light analysis on those edges to decide what we're committing to, what we're not committing to, and then pass forward any what at some point I called artificial defects, that are these defects that are due to the corrections that we commit to in only halfway through. But yeah, so principle easy as long as the decoder gives a set of correction edges.
Thanks.
Hi, I have a question. So you mentioned that your FPGAs have 500 megahertz. Which particular FPGA are you considering for that model?
Which, sorry?
Which particular FPGA are you considering having 500 megahertz?
Like the model? I think that's best to ask our hardware team. So I don't know the exact model numbers of FPGAs off the top of my head. But if you, maybe somebody from our hardware team can answer that question later on.
And I have another question. You mentioned that the data dependency between your windows, it's very low. But do you synchronize in any way these windows? And what happens if you have do you consider any Byzantine windows? Like
Any what window?
Like it's a distributed system, and one of the windows might behave in a Byzantine way, like lying about the corrections. Have you considered this?
Lying about the corrections, like being wrong?
Yeah.
So if there is an error that happened in any point in decoding, that is just then a logical error that ruins your decoder, ruins the solution of your decoding. What we showed here is that using this method, you don't have any increase in logical error rate if you use this method versus using just a global decoder, which is the best thing you can do given a particular inner decoder. So the accuracy is going to be given by what inner decoder you're using. And then this way of splitting it up is just the way to optimize the speed, but it doesn't affect the accuracy.
Well, we have time for one last question if anyone wants it. I see. Oh, in the back. Up high.
Hi, Luka. Thank you for the talk. A couple of slides back, you were showing the plots with the decoding frequency. Yes. So this is clearly something I've misunderstood because I'm looking. It's 0.4% physical, so I'm looking at the blue columns on the left. But I was expecting the serial line on the right to match the height of those blue columns. But what have I misunderstood?
I think, so the slight difference is going to be because of the way that the buffer regions work. Because when you're doing serial decoder sliding window, you're committing to exactly half of the window because of because of the buffer region size. When you're doing parallel window, there is a different buffer regions.
Okay.
So there is a slight difference there, but I believe that's the difference.
So maybe to ask that question a slightly different way, 9 by 9 by 9 is not 9 by 9 by 9 on either side because of the buffer region.
Yeah. I believe,
Okay. So the time axis here is different depending.
So here we're considering just 9 by 9 by 9 code. Here we're considering parallel window decoding with distance 9.
Yeah. With that, let's thank our speaker again.